Welcome to our deep dive into Chapter 10 of CBSE Class XII Physics, Dual Nature of Radiation and Matter. This chapter is a cornerstone for understanding modern physics, blending the concepts of waves and particles. Whether you're preparing for your board exams or building a foundation for NEET, mastering these ideas is crucial. We'll explore the photoelectric effect, Einstein's equation, the Davisson, Germer experiment, and practical numericals. Let's begin by setting the stage for why the dual nature of radiation and matter is so significant in physics. The photoelectric effect is a fascinating phenomenon that changed our understanding of light and matter. When electromagnetic radiation of a certain minimum frequency shines on a metal surface, electrons are emitted from that surface. This effect was one of the key pieces of evidence that light behaves not just as a wave, but also as a particle. The emitted electrons are called photoelectrons, and the process only occurs if the frequency of the incident light is equal to or greater than the threshold frequency specific to the metal. This discovery paved the way for quantum physics. A crucial aspect of the photoelectric effect is the threshold frequency. This is the minimum frequency of incident radiation required to eject electrons from the metal surface. If the frequency is below this threshold, no electrons are emitted, no matter how intense the light is. This observation could not be explained by classical wave theory, which predicted that increasing intensity should eventually cause emission. Instead, it highlighted the quantum nature of light, where energy is delivered in discrete packets called photons. Photoelectric effect follows several important laws. First, the threshold frequency law states that electrons are emitted only if the incident light's frequency is above a certain value. Second, the intensity law tells us that the number of emitted electrons is proportional to the intensity of the incident light, provided the frequency is above threshold. Third, the frequency law highlights that the kinetic energy of emitted electrons increases with the frequency of the incident light. Lastly, emission is instantaneous. Electrons are ejected as soon as the light falls on the surface, with no observable delay. The threshold frequency law is fundamental to the photoelectric effect. It states that for each metal, there is a minimum frequency of incident light below which no photoelectrons are emitted, regardless of the light's intensity. This minimum frequency is unique to each metal and is called the threshold frequency. If the frequency of the incident light is equal to or greater than this value, electrons are emitted instantly. This law underscores the quantum nature of light and the discrete energy levels involved in electron emission. The intensity law of the photoelectric effect states that the number of photoelectrons emitted from a metal surface is directly proportional to the intensity of the incident light, provided the frequency is above the threshold. This means that increasing the brightness of the light increases the number of electrons emitted, but does not affect their kinetic energy. This observation further supports the particle theory of light, as energy is delivered in quantized packets, and only those packets with sufficient energy can liberate electrons. Frequency law states that the maximum kinetic energy of the emitted photoelectrons increases linearly with the frequency of the incident light, provided it is above the threshold frequency. This means that higher frequency light not only causes emission, but also gives the ejected electrons more energy. This relationship is a direct consequence of the quantum nature of light and is quantitatively described by Einstein's photoelectric equation, which we'll discuss next. One of the most striking features of the photoelectric effect is the instantaneous emission of electrons. As soon as light of sufficient frequency strikes the metal surface, electrons are emitted without any measurable delay. This observation contradicts classical wave theory, which would predict a time lag as energy accumulates. Instead, it supports the quantum view that energy is delivered in discrete packets, and if a photon has enough energy, it can immediately liberate an electron. Albert Einstein provided a theoretical explanation for the photoelectric effect, for which he won the Nobel Prize. He proposed that light consists of photons, each carrying energy E equals h nu, where h is Planck's constant and nu is the frequency. When a photon strikes the metal, its energy is used to overcome the work function, Wi of the metal, and any excess energy is given to the emitted electron as kinetic energy. The equation is h nu equals Wi plus Kmax, where Kmax is the maximum kinetic energy of the photoelectron. Let's break down Einstein's photoelectric equation. The term h nu represents the energy of the incoming photon. Wi is the work function, the minimum energy needed to remove an electron from the metal surface. Kmax is the maximum kinetic energy of the emitted electron, which can be measured experimentally. This equation not only explains why a threshold frequency is needed, but also why increasing the frequency increases the kinetic energy of the electrons. It was a pivotal moment in the development of quantum mechanics. The maximum kinetic energy of the emitted photoelectrons can be expressed as Kmax equals 1/2, mv2 equals evi. Here, m is the mass of the electron, v is its velocity, E is the charge of the electron, and Vi is the stopping potential. This relationship allows us to experimentally determine the kinetic energy of photoelectrons by measuring the stopping potential required to halt their motion. It's a practical application of Einstein's theory and is often tested in board exams. Einstein's photoelectric equation was revolutionary because it explained all the experimental observations of the photoelectric effect. It showed that light energy is quantized and that electrons are emitted only if the photon energy exceeds the work function. This equation also provided a direct method to measure Planck's constant, a fundamental constant in physics. The success of this theory was a major step in establishing quantum mechanics as a new framework for understanding the microscopic world. Davisson, Germer experiment is a landmark in physics, providing direct evidence for the wave nature of electrons. In this experiment, electrons were accelerated and directed at a nickel crystal. The scattered electrons produced a diffraction pattern, similar to what is observed with light waves. This result confirmed that electrons, which were previously thought to be particles, also exhibit wave-like behavior. This experiment was crucial in establishing the dual nature of matter. Primary aim of the Davisson, Germer experiment was to verify the wave nature of electrons. By directing a beam of electrons at a nickel crystal and observing the resulting pattern, the experimenters sought to test whether electrons could produce interference and diffraction effects, phenomena typically associated with waves. The successful observation of a diffraction pattern provided strong evidence for the wave-particle duality of matter. Setup for the Davisson, Germer experiment included an electron gun to produce a beam of electrons, a nickel crystal as the target, a detector to measure scattered electrons, and a high vacuum chamber to prevent interference from air molecules. The electrons were accelerated to a known energy before striking the crystal. The arrangement allowed precise measurement of the angles and intensities of the scattered electrons, which was essential for observing the diffraction pattern. When the electron beam struck the nickel crystal, the scattered electrons formed a distinct diffraction pattern, similar to those produced by X-rays. This pattern could only be explained if the electrons were behaving as waves, with a wavelength comparable to the spacing between atoms in the crystal. The observation was a direct confirmation of de Broglie's hypothesis that particles like electrons have wave properties. Davisson, Germer experiment provided conclusive evidence for the dual nature of matter. Electrons, which were traditionally considered particles, were shown to exhibit wave-like properties under certain conditions. This discovery was a major milestone in quantum physics, supporting the idea that all matter has both particle and wave characteristics. It also validated de Broglie's theory and paved the way for further research into quantum mechanics. De Broglie proposed that all matter, not just light, exhibits both wave and particle properties. According to his hypothesis, the wavelength associated with a particle is given by lambda equals hp, where h is Planck's constant and p is the momentum of the particle. This idea was revolutionary and was later confirmed by experiments like Davisson, Germer. It forms the basis for understanding the behavior of electrons in atoms and the development of quantum mechanics. The de Broglie wavelength formula is lambda equals h/square root 2 μv, where h is Planck's constant, m is the mass of the electron, E is the charge of the electron, and V is the accelerating voltage. This formula allows us to calculate the wavelength of an electron given its kinetic energy. It's a key result that links the wave and particle nature of matter and is frequently used in numerical problems in exams. Let's apply the de Broglie wavelength formula to a practical example. Suppose an electron is accelerated through a potential difference of 150 V using the formula lambda equals h/square root 2 μv. We can substitute the values and calculate the wavelength. For V equals 150 V, the wavelength comes out to approximately 1 × 10 meters. This value is comparable to the spacing between atoms in a crystal, which is why electron diffraction can be observed in experiments like Davisson, Germer. When writing answers for board exams, it's important to follow a structured approach. Always start with the relevant formula, include all necessary units, and draw neat diagrams wherever applicable. Present your derivations step by step, making sure each step is clearly explained. This not only helps in scoring full marks but also demonstrates your understanding of the concepts. Remember, clarity and precision are key in physics answers. Dual nature of radiation and matter is a high-scoring chapter in the CBSE syllabus. Every year, questions worth 5 to 8 marks are asked from this chapter. It's also crucial for building a strong foundation for competitive exams like NEET. Focusing on this chapter can significantly boost your overall score, so make sure to practice all types of questions, from definitions to numericals and conceptual explanations. Let's quickly recap the key concepts covered in this chapter. We discussed the photoelectric effect and its laws, Einstein's photoelectric equation, the Davisson, Germer experiment, and the de Broglie hypothesis. We also looked at how to solve numerical problems using the de Broglie wavelength formula. Understanding these concepts is essential for scoring well in exams and for a deeper appreciation of modern physics. This chapter is not only important for board exams, but also forms the foundation for competitive exams like NEET. The concepts of wave-particle duality, quantum mechanics, and electron behavior are frequently tested in entrance exams. Building a strong understanding here will help you tackle advanced topics in higher studies and competitive tests. Students often make mistakes such as forgetting to include units in their answers, skipping diagrams, or not writing stepwise derivations. Another common error is confusing the threshold frequency with intensity. Make sure you understand the difference between these concepts and always double-check your calculations. Practicing previous years' questions can help you avoid these pitfalls. Let's try a practice problem. If light of frequency greater than the threshold frequency falls on a metal surface, what happens to the number of electrons emitted if the intensity of the light is increased? The answer is that the number of emitted electrons increases, but their kinetic energy remains unchanged. This reinforces the intensity law of the photoelectric effect. Here's another practice question. If the frequency of incident light is below the threshold frequency, will increasing the intensity cause electrons to be emitted? The answer is no. No electrons will be emitted regardless of how intense the light is, because the energy of each photon is insufficient to overcome the work function of the metal. Suppose the work function of a metal is 2 eV and light of frequency corresponding to 3 eV energy falls on it. What is the maximum kinetic energy of the emitted photoelectrons? Using Einstein's equation, K max equals h nu, Wi equals 3 eV, 2 eV equals 1 eV, this simple calculation shows how to apply the equation in exam problems. Let's solve a de Broglie wavelength problem. If an electron is accelerated through 100 V, what is its wavelength? Use the formula lambda equals h/square root 2 mv. Substitute the values for h, m, e, and v to find the answer. Practicing such problems helps reinforce your understanding and prepares you for exam questions. The work function, Wi, is the minimum energy required to remove an electron from the surface of a metal. It is a characteristic property of each metal and determines the threshold frequency for the photoelectric effect. Metals with a lower work function require less energy for electron emission, making them more sensitive to light. Planck's constant, h, is a fundamental constant in quantum mechanics, appearing in equations like E equals h nu and lambda equals hp. Its value is approximately 6.626 times 10^3 Js. Planck's constant sets the scale for quantum effects and is essential for calculations involving photons and de Broglie wavelengths. The photoelectric effect and related experiments demonstrate the quantum nature of light. Instead of being a continuous wave, light is made up of discrete packets of energy called photons. Each photon carries energy proportional to its frequency, and only photons with enough energy can cause electron emission. This quantum view is central to modern physics. Wave-particle duality is the concept that all particles exhibit both wave and particle properties. Light, for example, can behave as a wave in phenomena like interference and diffraction, but also as a particle in the photoelectric effect. Similarly, electrons show wave-like behavior in experiments like Davisson, Germer. This duality is a fundamental aspect of quantum mechanics. The photoelectric effect has many practical applications. It is used in devices like photoelectric cells, which convert light into electrical energy, and in light sensors, automatic doors, and solar panels. Understanding this effect is not just important for exams, but also for appreciating its role in modern technology. The discovery and explanation of the photoelectric effect marked a turning point in physics. It challenged classical theories and led to the development of quantum mechanics. The work of scientists like Einstein, Planck, and de Broglie revolutionized our understanding of the microscopic world and laid the foundation for much of modern science. To deepen your understanding, explore related topics such as the Compton effect, blackbody radiation, and quantum theory. Reading about these concepts will help you see the broader context of the dual nature of radiation and matter, and how these ideas connect to other areas of physics. Visual aids such as diagrams of the photoelectric effect setup and the Davisson, Germer experiment can greatly enhance your understanding. Drawing these setups helps you remember the components and the flow of the experiment, which is useful for both conceptual clarity and exam answers. Practicing stepwise derivations for equations like Einstein's photoelectric equation and the de Broglie wavelength formula is essential. Breaking down each step ensures you understand the logic and can reproduce the derivation in exams. This approach also helps in gaining partial marks even if the final answer is incorrect. The concepts in this chapter are foundational for modern physics. They connect directly to topics like atomic structure, quantum mechanics, and semiconductor physics. A solid grasp of dual nature and related experiments will make advanced topics much easier to understand in future studies. Including neat and labeled diagrams in your answers can make a big difference in scoring. Diagrams help illustrate your understanding and make your answers stand out. Practice drawing the setups for the photoelectric effect in Davisson, Germer experiment, as these are commonly asked in exams. To maximize your marks in this chapter, focus on understanding the core concepts, practicing numericals, and writing clear, concise answers. Time management is crucial during exams, so allocate time for each question and avoid spending too long on any single problem. Reviewing previous years' papers can also give you an edge. The dual nature of radiation and matter isn't just a theoretical concept, it has real-world implications. Technologies like solar panels, digital cameras, and even automatic doors rely on the principles discussed in this chapter. Understanding these applications can make the subject more interesting and relatable. Let's review the key formulas from this chapter. E equals h nu for photon energy, h nu equals Wi plus k max for Einstein's photoelectric equation, and lambda equals h/square root 2 me v for the de Broglie wavelength. Memorizing these formulas and understanding their application is essential for solving exam questions quickly and accurately. As we wrap up, remember that mastering the dual nature of radiation and matter is not just about memorizing facts, but about understanding the underlying principles. Focus on the logic behind each law and experiment, and practice applying these concepts to different problems. With consistent effort, you'll be well prepared for both board exams and competitive tests. Thank you for joining this comprehensive walkthrough of dual nature of radiation and matter. We hope this video has clarified your doubts and strengthened your understanding. Keep practicing, stay curious, and good luck with your exams and future studies in physics.